Have you ever really stopped to think about that little glass bubble over your head? The one that just beats the dark every single night? Well, today, we're going to unscrew that mystery and figure out exactly how a light bulb actually works. Seriously, go on, look up. That light probably feels like a tiny captured star, doesn't it? It's not magic, but it is a pretty brilliant piece of science. And today, we're going to pull back the curtain on this everyday miracle. You know, the story of the light bulb is kind of like a family saga. We're going to meet the old patriarch, the incandescent bulb, then its clever kid, the fluorescent bulb, and finally, the game-changing grandchild, the LED. So let's start at the very beginning. First up, the icon itself, the one you'd probably draw if someone told you to draw an idea. This is the original spark, the technology that first pushed back the night on a global scale. The principle here is actually pretty simple. Incandescence is really just a fancy word for getting something so incredibly hot that it starts to glow. Just think of a red-hot poker from a fireplace, or the angry glowing wires inside your toaster. That's the core idea. So how do you make a tiny wire glow? Well, you basically force electricity through it. This super thin wire, a tungsten filament, resists that flow of electricity. It fights back. And that struggle generates an insane amount of heat. We're talking over 2,000 degrees Celsius. At that temperature, it literally has no choice but to glow white hot, and boom, you've got light. Now, the beauty of this design was its simplicity. It was super cheap to make, which is why it stuck around for over a century. But here's the massive catch. 90% of the electricity it used was completely wasted as heat. It was less of a light bulb and more of a tiny, glowing space heater. And this glaring flaw is what sparked the search for a better way. So if making things super hot is the enemy of efficiency, how do you make light without all that heat? Well, enter the fluorescent bulb. This was a much more clever, multi-step process, a huge leap forward. The science here is called fluorescence, and you can think of it like a two-step magic trick. You basically take one kind of light that's invisible to us, and with a little bit of scientific sleight of hand, you transform it into light that we can actually see. Okay, so here's how the trick works. First, an electric current zaps some mercury vapor that's inside the tube, which gets the gas all excited. This excited gas then produces invisible ultraviolet light, or UV light. Then, that UV light hits a special phosphor coating on the inside of the tube. And this is the magic part. That coating absorbs the invisible UV and then re-emits the energy as visible light. And there you have it. This whole clever process is about 75% more efficient than the old incandescent bulb, which is a massive improvement. The only real downside, well, it contains a tiny amount of mercury, which makes getting rid of them a little tricky. And that brings us to the current champion of lighting, the undisputed king, the LED. Now, this isn't just an improvement, it's a completely different way of thinking about light. We're moving from glass bulbs and gases to solid-state computer chips. The principle here is called electroluminescence. Yeah, it's a mouthful, I know, but the name actually gives it all away. Electro for electricity and luminescence for light. It's making light directly from electricity, all happening inside a tiny little chip. Okay, this is where it gets really cool, right down at the subatomic level. When you send electricity into an LED, electrons inside the chip get a big jolt of energy, but they can't hold on to it. So they immediately release that extra energy as a tiny particle of light, a photon. Billions and billions of these tiny light bursts happen every single second, creating a steady, brilliant stream of light with almost no wasted heat. This direct conversion of electricity to light is, you guessed it, unbelievably efficient. And since there's no filament to burn out, these bulbs last for an incredibly long time. For a while, the only drawback was a higher price tag, but honestly, even that is becoming a thing of the past. So we've met all three contenders. Now for the fun part. Let's put them in a head-to-head showdown and see just how they stack up. Wow, okay, this chart pretty much tells the whole story, doesn't it? To get the same amount of light, an old incandescent bulb needed a thirsty 60 watts. The fluorescent did it with 15. But the LED, a mere 10 watts. That is a huge leap in efficiency. And if you thought that was impressive, check out the lifespan. An incandescent gives you about 1,200 hours of light. The fluorescent, a very respectable 8,000 hours. But a modern LED, a staggering 25,000 hours, or even more. I mean, that's a bulb that could easily outlive your pet. So let's put it all together. You've got the incandescent, light from a hot filament using 60 watts for 1200 hours. Then the fluorescent, light from excited gas using 15 watts for 8,000 hours. And finally, the LED, light from a glowing chip, sipping just 10 watts and lasting for over 25,000 hours. The trend here is, well, it's crystal clear.
If you take just one thing away from this, let it be this. The history of the light bulb is a journey from brute force to elegant efficiency. We've gone from making light by making heat to just making light itself.
We've gone from brute force heat to subatomic precision. Light is now cheaper, more efficient, and more abundant than at any other point in human history. So the final question isn't really how it works anymore, is it? It's what will we choose to do with it?